Welcome to the sandbox, developers. If you've ever written a piece of code that works flawlessly on a tiny dataset but literally freezes your machine the second you try to scale it up, well, you know the absolute frustration of hitting a mathematical wall. Today, in this explainer, we are coding our way right out of that trap. We're going to look at how we can use approximation algorithms to completely bypass exponential wait times while still guaranteeing incredibly powerful results. So here's the roadmap for today's explainer. We'll start by dissecting the trap of perfect code. Then we'll define our mathematical limits with the approximation ratio. After that, we'll step through two actual algorithm tutorials, the vertex cover and the traveling salesman. And finally, we'll prove exactly why good enough wins out in the real world. All right, let's jump straight into section 1, the trap of perfect code. This is the fundamental bottleneck we hit with NP-complete problems. Look at the sheer scale of the problem we're dealing with here. Trying to perfectly solve a complex routing or grouping problem requires exponential runtime. We're talking theta of 2 to the power of n, or n to the power of n. Yikes, right? If your input size is tiny, sure, your code finds the answer in a snap. But as your data grows to just a few dozen points, a standard server could literally run for millions of years before finding the mathematically perfect result. That is the trap. On the flip side, we have approximation. This approach computes a nearly optimal solution efficiently, in polynomial time. It's basically a developer cheat code to get an answer right now, instead of at the end of the universe. To put this into perspective, just think about a massive global delivery company. Waiting for a server farm to calculate the absolute flawless shortest path for 10,000 packages is frankly impossible. Those trucks would never leave the parking lot. But by utilizing a polynomial approximation, you get a highly efficient, near-optimal route that gets trucks on the road immediately. You're trading an imperceptible loss of routing perfection for a system that, actually functions, saving millions in computing costs along the way. Moving right along to section 2, the approximation ratio explained. Before we open our IDEs and start writing pseudocode, we need a mathematical standard to measure our work. Just how good is near optimal? Enter the approximation ratio, denoted by the Greek letter rho. This isn't just a rough estimate, it is an ironclad, guaranteed performance bound. It directly compares the solution we compute against the mathematically true optimal result. And the absolute magic of this is that the ratio holds true even if we have no idea what that optimal result actually is. Notice how this scales based on what you're trying to do. For maximization tasks, you divide the optimal result, let's call it C star, by our computed solution, C. If the absolute best score out there is 100 and we hit 50, our ratio is 2. For minimization tasks, like keeping costs low, we just flip it. We divide our computed solution, C, by the optimal C star. If our route costs 100 and the impossible perfect route costs 50, our ratio is again 2. When you realize your code is mathematically guaranteed to never be more than twice as bad as absolute perfection, it's a real aha moment. You've successfully bounded the chaos. Okay, let's get our hands dirty in section 3. It is tutorial time, focusing on the famous vertex cover logic. Picture a vast network map in front of you, maybe a massive grid of computer servers. The vertex cover problem asks us to find the smallest possible subset of vertices, or server nodes, that touches every single edge connecting them. Basically, we want to minimize the number of nodes we select while making absolutely sure that every single connection line in the whole graph is securely anchored to at least one of those selected nodes. Let's step through the algorithmic loop together. First, we initialize an empty set for our cover, let's call it C, and we load in all our edges. Next, we select a completely arbitrary edge from the pile and add both of its endpoints to our cover set C. Then, and this is the really clever bit, we strip away every single edge in the entire graph that touches either of those two nodes. They're locked in, so their connections are officially covered. Finally, we just repeat this loop. Blindly pick an edge, clear its neighbors, and keep going until the graph has 0 edges left. And what is so brilliantly efficient about this approach? The runtime. It's big O of V plus E. That means our execution speed is strictly limited by the number of vertices and edges in the network. We aren't testing every possible combination of nodes, which, remember, is an exponential nightmare. We just walk through the graph once, pluck edges, and clear adjacent lines. It's incredibly fast and scales beautifully. So how do we mathematically defend this? Let's take it slow and break down the logic. Let's call the arbitrary edges we picked set A. Because of how our loop works, every edge in set A shares absolutely no vertices with the others. They are totally independent. Because of that, even the magical, perfect optimal cover, C star, has to pick at least one node for every single edge in A. So we know C star is greater than or equal to A. But remember, our algorithm simply grabbed both endpoints for those edges, meaning our cover size, C, is exactly twice the size of A. By substituting those variables, we prove that our cover is at most twice the size of the true optimal cover. We secure a guaranteed ratio of 2 without ever needing to find the perfect cover. How cool is that? Next up, Section 4. Let's tackle an even more infamous sandbox challenge, the traveling salesman route. The traveling salesman problem, or TSP, is basically the holy grail of logistics algorithms. The objective is to find a minimum cost round-trip tour that visits every vertex on a graph exactly once. For our approximation, we're going to assume the triangle inequality holds true. That's really just a formal math term for a common-sense hack. Taking a direct, straight-line shortcut between 2 points is always cheaper, or at least equal to, taking a weird detour through a third point. Watch how elegant this transformation is. First, we pick a root vertex. Second, we use MST prim to build a minimum spanning tree. Think of it as a web of the absolute cheapest edges connecting all nodes without any loops. Third, we do a pre-order walk. Just imagine tracing your finger around the outside edges of this tree to list out the vertices in order. Finally, we translate that tree walk into a valid tour by drawing direct lines and skipping any nodes we've already visited. Now, the bounding logic here is fantastic. A full pre-order tree walk goes down every branch and then comes back up, meaning it visits every edge twice. So the cost of our walk, W, is at most double the cost of the impossible perfect route, H star. But remember that triangle inequality? By taking direct shortcuts and skipping over the nodes we've already seen, we actively shorten our final route, H. Turns out, cutting corners is mathematically sound here, so our final cost is guaranteed to be less than or equal to double the perfect route. Once again, a brilliantly proven ratio of 2. Which brings us to our final stop. Section 5. Why good enough wins. Let's look at why these guarantees are an absolute superpower in real-world development. Just contrast the two methods we walked through. Whether our goal is to strip away edges in a complex network for a vertex cover, or we're walking spanning trees to map out a traveling salesman route, the underlying philosophy is the exact same. Both of these polynomial approaches miraculously bypass those dreaded exponential wait times. We trade the illusion of absolute perfection for concrete mathematical certainty, locking in a guaranteed performance ratio of 2. It's reliable, it's highly scalable, and most importantly, it actually works. So as you head back to your own development projects today, I want to leave you with a question to chew on. Where in your own code base are you burning precious server resources and your own time chasing an impossible optimum? Sometimes the absolute best code isn't the code that finds perfection, it's the code that realizes an approximation is all you really need. Thanks for joining me in the sandbox today, and happy coding!